set membership approach to the kidnap robot problem. This work has been done by Benoît Desrochers during his internship with Simon Lacroix in Toulouse and has been presented at the iros2015 conference that took place in Hamburg. In this problem, we will deal with the initial localization of a robot equipped with a LiDAR, and interval analysis will be used for this purpose. I first present the Omne estimator, which has been introduced something like 30 years ago in the context of set membership estimation. So first, I should recall that the localization problem, initial localization problem, can be formulated as follows. I have a P which corresponds to the parameter vector, but for us it will be the position of the robot. A function fi, where I corresponds to the ith measurement, and the interval yi corresponds to the ith collected interval data. I will also note by p star the true value for the parameter vector p. And the objective is, from all these measurement intervals, to estimate the true value p star for p. I will use this following notation. I will denote it by pi, the set which corresponds to all parameter vectors which are consistent with the interval yi. So it can be denoted in a set inversion formulation. It will be the inverse by the function fi of this interval. I will also define what is an inlier and an outlier. An inlier, so the interval yi, so corresponds to the measurement, is an inlier, is for the true value for p belongs to this set. It will be an outlier if it is not the case. So now I have all the tools to present what is the Omne outlier minimal number estimator, where the estimator tries to minimize the number of outliers for the parameter vector. It has been presented by Walter and Lanier in 1987. So if I have a parameter vector p, I will denote by lambda of p the number of measurements for which p is inconsistent. Okay, recall that if p does not belong to pi, it means that it is not consistent with the interval yi. So of course, I want to minimize lambda. And I will denote by q star the minimum I can reach for lambda. I hope indeed that for p star, I will the number q star will be small because I will be consistent with many data. And Omne estimator returns the set p, which corresponds to the inverse, to all parameter vector, which are consistent with q star. So it corresponds to the inverse by lambda of the integer number q star. It is the Omne estimator. The main problem with Omne is to compute it. In Lanier and Walter, they use Monte Carlo technique, and a guaranteed omni has been proposed using interval method. For this, I need to formulate omni in a set membership formulation. For this, I will need the concept, the notion of Q-relaxed intersection. I consider in the parameter space uh, the sets that are consistent with the ith data. So in this picture, I have 6 data, so 6 sets. As we can see, there is outlier. I can recognize that there is outlier because this set, these 6 sets, has no intersection. So the intersection of the 6 sets are empty. So the idea of omni will be to relax some of them, and I can define the 2 relaxed intersection as the sets of all p that are consistent with all pi except 2 of them. So I relax 2 of them. And if I do this, I define in red here the relaxed intersection corresponding to Q equal 2. The 3 relaxed intersection is in this sub-picture. So it contains all points that are consistent with all sets except 3 of them. And here the 4 relaxed intersection on the last picture. The 5 relaxed intersection would correspond to the union of the 6 sets. Okay. So now I have defined the relaxed intersection. Omni corresponds to what? I recall that pi corresponds to the inverse by fi of this interval, of the data interval. And I define pq as the intersection, Q-relaxed intersection of all pi. I define q star as the minimum I can reach for q, such that the relaxed intersection is empty. So in my previous example, q star corresponds to 2, because if q equals 1, I am empty. If q equals 0, I am empty. So q can be equal to 2, 3, and 4, 5, and so on, and I will not be empty, and the minimum of them will be 2. So q star the minimum of the q, so that I am not empty, and omni will return the p corresponding to q star. This can be solved using interval methods in a guaranteed way, and it is the objective of the outer omni, which has been proposed by Benoît Desrochers. I will now give an illustrative example. In this example, I have 3 landmarks, and I can measure the distance between these 3 landmarks. To illustrate this, I will take a small Python program that has been made by Benoît Desrochers, and will use vibes for the graphism, and we'll use also PyBex. So PyBex is a library which is based on ibex, which make it possible to handle interval analysis tools such as contractors or separators. I first define the position of my landmarks. So here I consider 3 landmarks. I define also the distances that I measure. So here it will correspond to my interval measurements. And I translate all this information into separators. So I do not explain here what is a separator, but in short, it is a tool which takes a box as an input and returns 3 and decomposes into 3 parts. A part which is enclosed in pi, one a part which is outside the set pi, and the other part for which I don't know if I am inside or outside. So I define all the separators associated with my pi, and I have here an array of separators, which is called seps. And I call a paver, and I will be able to draw the set PQ, where Q is initialized here. So here I initialize with 0. It means I will do the intersection. So let me run it. Uh, so here is represented the three, so the landmark here, here, and here, the three rings corresponding to the interval measurement. And here I have the intersection. So I am in a case here where I have no outliers. I can guess I have no outlier. And Gomne will return me this set. Red means inside, blue means outside, and yellow is on the boundary. Now, if I take another Q, for instance, Q equal 1, then the same procedure will provide me the one relaxed intersection. So here I belong to at most two rings, here to three, but so the two relaxed intersection will return me the red set. Again, the frontier is in yellow. And for Q equal to 2, so I have to reject only one of the set, and I will obtain the union of the three rings, which is given here. Okay, so it means that if I accept two outliers, then the Gomne or the interval method will tell me that my robot is inside the red area. So of course here Gomne will return me 0 for Q star because the intersection exists. Now let me add an outlier. For instance, this one. I will put my out. For instance, the landmark, the second landmark will be here. If I try to draw for Q equals 0, the interval method will return me the empty set, which is lies here. I have no solution. If I set Q equal 1, then the intersection exists, and Gomne will return me the set represented here. Okay, here or here. So two solutions. Of course, everything which is shown here can be done using Monte Carlo method. But here I have the guarantee. And on each blue box, I have the guarantee that I have not a single solution. And the computation time it takes for one box is about the same 10 times what the computation that has to be done for one point. So if I take a particular method, I will have to take many points inside, and I will try to be attracted by this red area. But of course, in my application, it will be interesting to mix the particular method or Monte Carlo method or local search with interval method. Interval method will be perfect to eliminate bugs where I have no solution, and particular filter method or Monte Carlo method will be perfect to be attracted by these zones. I will need to define what is a digital elevation map. So for us, it will be defined as a set, the set of all points that corresponds to an obstacle. So if you want, it corresponds to the complementary of the free space. I will call it a map. I will denote it by M. It can be taken, for instance, by a drone, which fly over houses, like here, and equipped with a LiDAR, it will be able to build this kind of map, which is called ortho image, aerial ortho image. So I can recognize here a tree, and since the plane is at the top, it will not be able to see below the trees and also below the houses. In practice, I can also use here a wheeled robot, which is here a wheeled robot of the LAS in Toulouse. And this one is equipped with a LiDAR, a Velodin LiDAR. So it will be able to see all the walls, but it will not be able to see at the top. For instance, here we can recognize in white the top of a tree, and this robot is not able to see the top of the tree, but it can be mixed with data recorded by the plane. Okay, the color corresponds to the altitude here. When I want to localize, when the robot wants to localize, it will use, so it will be a wheeled robot, and the wheeled robot will be able to collect this kind of data with Velodin LiDAR. And since to avoid to handle too many data, I will first have to compress this data. So it will be the down sampling represented here. And then I will only select the vertical part because this contains the information that will make me possible to localize. What about the localization? I will the unknown will be x, y, and c, where c, so xy corresponds to the position, xy position, horizontal position of the robot, and c corresponds to the heading. Then I will denote by pi the set of all p that are consistent with the map, but also to the if function. So this one corresponds if I know where is my robot. Using the function fi, I will be able to compute from m where should I the distance to the map that should be written by the LiDAR. Of course, in fi you have the Euler angle, the two other Euler angles that do not correspond to psi, as the roll and the pitch. I define once more this set P where Q is relaxed. I minimize it, but I try to be consistent, so no empty set, and that's what I will do here. So in this application, I only show another example, a small example, but several examples are given in the paper. So in this example, everything works quite well, and my robot is here. I have a good localization, and in green I can see the inlier. If I assume so that, and in red the outlier detected by Gomney. Here we can see that some outliers given here in red, probably they could not have been considered with as outlier because they are consistent with the blue area which corresponds to houses. But what I wanted to what we wanted to illustrate here is that the approach, of course, we can use a Monte Carlo method for this, but the main advantage of this method it is guaranteed. I mean, it will find the global minimum.